Okay. So section 3 is talking about proving identities. So we're going to start with some like rules and tips and suggestions about how to go about doing this. Now I notice, or you guys probably have noticed the P word here in the title being proving, and maybe you're having a bit of a panic attack going on because you're like, I can't do that. You will be just fine. If you could do section 1, where you did the simplifying the trig expressions, this section I think is actually a little bit easier. It's essentially doing the same thing, but this time you have like an end, you know what the end should be. Okay? So going through these tips and requirements, we're going to start on one side of the problem and then keep working at it until you end with the other side. We're not going to allow you to do the same operation on both sides of the equation, so you can't change both sides. You're going to just pick one side and work on that one side. Everybody okay with that idea? Typically, you're going to want to begin with the more complicated expression and work towards the simpler expression. Do you have to do it that way? No. You can go either direction, complicated to simple or simple to complicated. In general, though, most of us do better like simplifying and canceling things down than they do like building things out and making it more complicated, but there's no reason that you couldn't work from the other side. If you get stuck and you're unsure what to do, you can convert everything into sines and cosines. That's usually helpful. If you have to combine fractions, you need to remember to get a common denominator. The identity a plus b times a minus b is equal to a squared minus b squared is very useful. What is the name for that identity? We talked about it last year in the algebra course. A plus b times a minus b equals a squared minus b squared. That had a name. Does anybody remember that name from last year? We used an acronym to describe it. It was dots. That was the difference of two squares. Right. That guy right there. And that's often going to be useful in creating a Pythagorean identity. Remember the different versions we had, like 1 minus cosine squared or 1 minus sine squared? Those are a squared minus b squared, right? It's something squared minus something else squared. So it's often helpful to remember that we can create those in that fashion. And the last tip here says, always be mindful of your target expression you're working towards. By that I mean it's often helpful to pick your head up and kind of look at what your end is supposed to be. Because oftentimes the ending is going to help inform you as to what you would want to do next. Like there's a goal in mind. Should be try to be working towards that goal. And for the rest of this lesson, we're just going to do some examples. Sound good to you guys? Are we ready to start the examples, or are people still writing? Okay. I tried to read real slow, but apparently you're writing slower today. That's okay, though. Yeah. Mm-hmm. How about now? Are we ready? Okay. It's about the same as the first one. All right. So the first thing we want to do is want to make a decision about which side we want to start on. So we want to start on the more complicated side. Which side is the more complicated side? The left side or the right side? Okay, so some people said left, some people said right. The answer to this should be the left side. Why is the left side more complicated? Nope. It's because we have two things being added together here. On this side, we have one thing. 2 is more complicated than 1. Think about it as terms of a polynomial. Like x plus 2 is a more complicated polynomial than just like x, right? So that's why we would want to start with the left-hand side, is because we really have two things that are being added together. On the right-hand side, we just have one thing, one term. Is that, you guys can see that? So let's work on the left-hand side. And I'm going to ask for you guys to kind of help direct as to what to do. So you'll probably want to have your identity sheet out to look at. It will probably be helpful if you don't have those identities kind of memorized already. Again, you would not be required to have them memorized for anything, but we've done a fair bit of work using that identity sheet, and if you're starting to remember some of these common ones, that would be good. Okay. So we're working on the left-hand side, and we want to turn it into the right-hand side. The left-hand side is tangent x plus cotangent x. What do you want to do to try to get those or what do you want to do with that? Hannah? Okay, so Hannah's saying maybe I'll rewrite cotangent as 1 over tangent. Okay, that seems reasonable. We can do that. So just FYI for you guys, I'm going to work vertically down this for these kind of problems as opposed to the simplifying problems where I kind of worked horizontally. So here there's two sides of the equation. The right-hand side I'm not going to recopy. It's just going to stay the same. The left-hand side is the side I'm changing, so that'll be the side that I rewrite each time. Okay, so we did that using R6. Okay, what should we do now? Add them. Great. What do I need to do to add them? I need to make a common denominator. What would the common denominator here be? Tangent x, right? So the first guy, I need to multiply by tangent x over tangent x. And then I would have a common denominator between the two. It would look like this. Everybody agree with that? Yeah, I just wrote it all as one fraction. Okay, that's fine. What would you like to do next? Well, if you do that, you're going to end up back at the previous step. Because all you would do is get rid of the common denominator, if that's what you're asking to do. I would not do that, because we just went through the trouble of making the common denominator. Probably not what I would use here. Look at that numerator. Madison? Yeah, so if you look at P3, P3 says tan squared plus 1 equals secant squared. That seems like a good choice here, particularly since I know that I'm supposed to have secants in the final result here. Yeah, that the opposite side is where we're supposed to end at. So I'm going to kind of keep that in mind as I'm going. Yeah, the other side is not going to change. We're just trying to make the left-hand side turn into the right-hand side. It's all we're trying to do here. Everybody okay there? And in fact, if we really wanted to think about this, we could think about it as secant x times secant over tangent. Why would I want to think about it this way? What's the answer supposed to be over here? Yeah, we're supposed to be getting secant times cosecant. And look at what we've already got. Right? We've got the secant part already taken care of. So somehow, secant over tangent needs to turn into cosecant. I would probably not use an R here. Which Q? Which version of Q1? The secant over cosecant one, right? So I know you have a question, Lexi. I'm going to finish this up and then we'll circle back to it, okay? We're just very close. What was your question, Kendall? No, I was just pointing out to you guys that like this is one of the advantages of like go back and look at what you're trying to get to, because we got part of it, right, with that previous step. It's like, oh look, there's a secant. Let me just separate that off to the side so I know I don't want to mess with that anymore. And I know that the other part that I want to get is going to come out of this other piece somehow. Does that kind of see what I'm getting at there? Okay. Yeah, so how would I simplify that? Well, this is two fractions that are being divided, right? Because really the top is like secant over 1. So how do we divide two fractions? Yeah. we see those guys cancel out. And we're left with exactly what we're hoping to get. This should end up being easier than the section 1 questions, because here we know exactly what the answer is supposed to be. In section 1, you didn't know what the answer is supposed to be when you started. You're just hoping to get it down to a single trig function, and then you're like, okay, I know that's as good as I can do. But here we don't know, or here we know exactly what the end looks like. So you know when you're finished, you know what to work towards. I think these problems tend to be a little bit clearer in terms of what to do, because you have a goal in mind when you start the problem, if that makes any kind of sense. Okay. Was this the only way you could have done this problem? No, right? Had you picked different identities in the beginning, you could have done this slightly differently. I think it might even been a touch faster, but what you guys did was perfectly reasonable. Lexi? If you multiply something by its reciprocal, you get 1. This sounds a little bit specific, and maybe it's something you and I should look at here in a minute, individually, rather than right now in front of kind of the whole group, because I think you have something very specific in mind. I'm not really even positive what you're driving at right now, so I'll certainly be happy to talk to you about whatever's going on here in just a minute, but I'm not positive what we're asking for, so yeah. And again, if you want to look through your stuff and you figure out exactly what it is that we're looking at, be happy to help. Okay? Sure. Okay. So let's look at this next identity. Cosine n over 1 minus sine n equals 1 plus sine n over cosine n. Which side looks like the more complicated? They look pretty similar, so it probably doesn't matter here, right? Okay, so for the sake of argument, let's just start with the left-hand side. Sound good to you guys? Okay. Hannah. It can certainly have an impact, it might be one side might be trickier to get to work than the other. But no, it doesn't, you can do it using either side. Not if things are correct. In general, I want to say that you typically is easier to start with more complicated and go to less complicated. Here it doesn't really matter, because if you look at these, they look about the same, right? Okay. Ideas on what to do here first. Well, you don't have anything squared, right? So So you can't do a P1, but I do think that one of the Pythagoreans would eventually be helpful. Is there a way for me to make this turn into something I can use a Pythagorean identity on? Go back and look at tip number 5. That was the dots one. So let's try to make the denominator into a difference of 2 squares. What would I need to do that? No. You can't just square the denominator of a fraction. But we can do that and multiply the top and bottom of the fraction by 1 plus sine n. Everybody, why would I do that? Well, why can I? Because all I've done is multiplied it by 1, right? 1 plus sine n over 1 plus sine n just reduces down to 1. And I can multiply anything by 1 anytime I want because it doesn't change anything. This has the added bonus, the left-hand side, or I'm sorry, the right-hand side where we're trying to get to, I have to have a 1 plus sign in the numerator. When I do this, what am I going to end up with in the numerator? A 1 plus sine n. So this is like a doubly good idea. I'm going to get a situation where I can use a Pythagorean, which seems like it's probably going to be useful, and it gives me something I'm already looking to have happen in the numerator. Kendall? Are you sure?
Yeah.
Okay. So, if I rewrite this then, should I distribute the cosine through to that 1 plus sine n? No, why not? I need that 1 plus sine n to be by itself. Somehow this cosine I'm going to need to have cancel out. Not quite sure how that's going to happen, but I know it has to happen, right? Okay, and then what should I do with the denominator? Should I multiply that part out? Yes, because what's it going to give me if I multiply it out? A Pythagorean, right? So if I use that difference of 2 squares, I'm going to get 1 minus sine squared n. If you don't trust me that that's what you get when you FOIL it out, you could FOIL it out for yourself. But I promise you that's what you get. Everybody okay to hear? Look at the 1 minus sine squared n. Do you recognize that? What does that turn into? Cosine squared. Good. Everybody good with that? And what do you see can happen now? Yeah, we can reduce. And what are we left with? The left-hand side, or the right-hand side. And we're done. Yeah, Kendall? So, not really. So at some point you're going to have to kind of do that. Had we decided to work with the right-hand side, you could have rewritten that as like 1 over cosine plus sine over cosine, and then tried to monkey around with that. But I think that at some point you're going to have to end up doing something. Yeah. I don't know that there was a way around having to do something tricky on that one. But part of the reason we're doing these examples is to like show you things that you can think of trying, right? Yeah. So if you have fractions like this, sometimes if there's no common denominator to make, making a perfect, like a difference of two squares so you can use a Pythagorean is a good idea. So again, like having never seen this before, it's hard to come up with that as a suggestion. Having seen that you can do this before, hopefully that goes into your like things to try bin. You know what I mean? Yeah. You're welcome. Okay, how about this one? Which side would you guys like to try to work on? The right? The left. Yeah, I think all of us would agree the left is a bit more complicated than the right. Okay. What would you like to do first on the left-hand side? Well, you can't. Yeah, let's FOIL those out. When we FOIL out the numerator, what's going to happen? Is everybody okay with that? And again, I FOILed that out in my head because what is this? That's a difference of two squares situation, right? Anybody with ideas what to do next? Uh-huh. Yeah, what does 1 minus cosine squared turn into using our modified P1? Sine squared. Okay. Yeah, and then we know that sine squared over cosine squared is tangent squared. And that's the other side. That's it. So some of them from the beginning look pretty gross, but turn out to not be so bad, right? What was nice about that is we didn't have to worry about making any common denominators or like screwing around with any fraction, tricky things. We just multiplied stuff out and went through two identities and we were done. It was pretty painless. Take a look at this one. I think that's a wise idea. Okay. And what would you like to do first on the right-hand side? I don't remember if we took this from another textbook or if we made this ourselves. What do you want to do first to that right-hand side? Well, if I look inside the parentheses, I have a sign squared, a sign to the fourth, and a sign to the sixth. So none of them are like terms. Yeah. What could we take out? Yeah, let's take out a sine squared. Good idea. Mm-hmm. No, that's true. So we made the observation here that now we have the sine squared a part. Everybody agree with that? And we have a cosine A already, so somehow this part is going to have to turn into cosine to the fourth. Everybody agree with that? Okay. Because we already have the other cosine sitting there, and that's how we're going to get the cosine to the fifth. So all we're going to worry about is that part in green, trying to get that to turn into a cosine to the fourth. 1 minus sine squared is equal to cosine squared. That's true, but we don't have either. You want a hint as the easy way to handle this? That part in green factors. Imagine if I look at it as one minus 2y plus y squared. That looks like something that's factorable, right? How does that factor? We're trying to, you see how this is the same as that, right? So let's factor 1 minus 2y plus y squared. How does that part factor? So we need two numbers that multiply to give us 1 and add to give us negative 2. Negative 1, negative 1. So it's probably tempting to write it this way, right? But remember, we'd have y is sine squared. So you'd have sine squared minus 1. How would we prefer that to be written, though? Probably prefer to have 1 minus sine squared, right? So the other option that still multiplies out to give us the same thing. So if I write it that way, that's the way that I prefer to write it. Okay. Now what should we do? I'm staring you right at the face, guys. Right in your little faces. I can't cross anything out. There's no denominators. Hallie, can you say that louder so everyone can hear it? That's a good idea. Because what was that piece in green? What did we need it to turn into? To the fourth, right? And what do we have there? It's 2 cosine squareds. Yep. And now that when we multiply those guys all together, what are we going to get? To the fifth. And we're done. We have this class again tomorrow. Sure. Jeepers creepers, you guys. So for next time, let's try to do 47 to 54.